Hello, we are back now to wraps up what we left off from the last clip. Okay, clip number 28. Now we're starting the clip number 29 with the last line of the file simplex metric form. Okay, uh, I think the content start way back from clip 25 about we talking about the simplex method in metric form. Okay, and we be able to identify the notation of the reduced cost coefficients uh, and also okay the simplex uh, uh, entering a leaving variable. Okay, and optimality condition leading to the relationship with the weak and strong dualities in metric form. And we use this result to develop an approach to handle the LP when there's a large number of constraints as compared to the number of decision variables. And or in the reverse case, in the dual form, the problem becomes the LP with too many variables, with number of large amount of decision variable as compared to the number of constraint. And we left off with the last slide here. Okay, last time. Okay, that suppose we have a simultaneous case of too many constraint and variable at the same time. Okay, this might lead you to difficult situation, what we call when the constraint matrix A is out of core memory handling. Okay, can we solve this problem efficiently and effectively? Effectively is mean that guarantee the optimal solution. Efficiently mean that okay, you can solve a very large problem using the available limited hardware, which is rarely happen nowadays anyway. Okay, and uh, we're gonna show you some example. Okay, we already show you illustrate you with both the Excel and the Matlab. Okay, I think that today we will discuss and give you an idea of a Matlab example extension from the previous study. Okay, and we're gonna go move to the Matlab environment. Okay, actually I already installed a file called Thanapan code LP both large and capital M and N, which is a number of variable as compared to our previous okay program of LP too many constraint row generation. Okay, we have tried with a very large number of row represented by the amount of capital M. And the other one is the column generation with the number of variables represented by capital N. Okay, and also we have a benchmarking file of code of the LP direct solving. And I think we created the new code down here of Thanapan code, which already been installed in the folder 3 folder of lecture 3 here. Okay, we have a Thanapan code down here. Okay, actually you know that the guy who code this program is supposed to be Dr. Thanapan Kong Thong. Okay, lecturer at the Industrial Engineering เกษตรศาสตร์ University of กำแพงแสนnoศรีราชา campus. Okay, he coded this while he's studying the PhD program at เกษตรศาสตร์ University บางเขน campus. Okay, and I think it was a very interesting idea. Okay, so we're gonna take a look at how his code look like. Okay, and I think that we have to go back and consider the idea of row chain and column chain because we have to mix these two all together. Okay, Uh, the key is that for both low gen, let's look at the low gen first. Okay, low gen, you need to develop this loop. Okay, do while here. Okay, by solving a much smaller LP. Okay, but in sequentially with every time a new row, a new additional constraint has been added. And we expect that when we solve the sequence of a much smaller LP, okay, the problem toward the end and the final solution, the resulting model wouldn't be that big. It means that you didn't use all the constraint. Okay, you use a much smaller amount of constraint as compared to the whole problem. The same work for the column chain also. We develop a loop here. Okay, instead of adding a new row, we're adding a new column one at a time. Okay, and the result, as you already show on the last two clip, okay, that you can work both on the Excel platform or in the Matlab platform. Okay, I think Dr. Thanapan once saw these two programs. He developed used the idea of these two programs to develop this program. So the notation is quite pretty similar, the same, by mixing up, okay, both programs together, which was a clever idea. Okay, let's see the logic how he developed the approach to solve the problem. Okay, first, okay, now you have both small m and n notation. Start with the 10 constraint and 20 decision variable as compared to the original problem that actually capital M and N need not to be equal. Okay, just in this case. In this case, we have a 10,000 constraint and also 10,000 decision variable. And also remember that we're working on the inequality issue. So in this case, M and N need not to be equal. Okay, this is my, but just a setting for this illustration. Okay, and also we have a full. Okay, which is full matrix. Okay, so this is not still not working very well here in terms of memory management, because with this large, luckily in my computer we can still run with the size of 10,000 by 10,000. But we increase it 10 times more, become 100,000 by 100,000. It's gonna run out memory unless that you use a new computer or the kind of server stuff that you can have a very large amount of hard disk drive. Okay, not the hard disk drive. This time has to be the RAM. Okay, that sufficient with sufficient amount of RAM memory. Okay, to store. And also we have a small matrix of A column and A row. As you probably be recognized that why we need this line 8 and line 9 in the program. Okay, because this is a sub vector. A column is mean that the sub problem based on only small m and all decision variable capital N, and A row is by considering all the constraint capital M and only a partial number of decision variable small n. Okay, this one is but our really problem that we're gonna solve is only using the A sub here. A sub is only small m and small m and small n. Okay, we keep adding it one at a time during the iteration process. Okay, so the whole idea is just to combine these two programs, row gen and column gen, together to working on this. Okay, and certainly B and C have to use cover all right hand side constraint and all cost coefficient or profit coefficient in this case, because we're working on the maximum problem. Okay, and certainly we have C sub only sub part and B sub. Okay. Now we randomly generate. Okay, for the right hand side, and this is for the A full. Okay, and after we have a full matrix of the constraint, okay, we partially, okay, transfer this data to the A column here and the A row here. Okay, so a column, okay, will be the submetric used in the column generation routine. And a row is a full matrix, okay, used in the row generation routine, okay. And both are the submetric from the a full here, okay. And this one we generate all the cost coefficient and use the minus sign because certainly with less than or equal default constraint in Matlab linprox command, okay. Is this time we want to work on the maximization of CJ on the reverse sign, okay. And a sub here, okay, we use it the initial. This is not the initial good initial point. We just pick the first m and the first small m and small n here, okay, not the capital one, okay, for to use as a sub. And with this randomly generation is already guaranteed that you have an initial feasible solution, okay, with b sub here and c sub here. So after 45 line, we have enough for the setting up, okay, for setting up the problem, okay. And it might took a while because as compared to the previous either row gen and column gen program, because we need to combine all the setup of these two programs together. Okay, and the next step is we coming to the loop part that combine the two programs together. Okay, the idea of Dr. Thanapan is that, okay, we start with counting the number of iteration, ITR, and certainly we use the min RC, okay, minimum reduced cost coefficient for both primal and dual model. Start with a large negative value, okay, and but as if that still exists, the negative value, okay, we're gonna keep adding up either the new variable or the new constraint, okay, not just purely row or purely column like the board program that we already did here. Okay, so the idea is that, okay, they start counting line 32, start counting the iteration, and every time, okay, the new variable been added, we need to reset up the L parameter here, because L is the lower bound for the n program, because if they're facing up the new column gen here, n equal n plus 1, okay, the new lower bound need to be reset, okay, for as a part of the attribute for the linproc procedure here, okay. And we solving the corresponding LP, the much smaller LP, okay, as compared to the last one, okay, and which in this case you have both too many constraints and too many variables. And okay, since this is a column gen, okay, we have to go back to Thanapan code here, okay, the similar way, okay, iteration and the L need to be reset up every time, okay. And in this case, once we solve this problem, okay, we're gonna get the optimum solution store in X, okay, and the dual variable store in lambda. And we have two different type, okay. For you remember RCC1 is from the column gen, okay, this one RCC, okay. From row gen, the RCC is in this form, the right hand side minus the left hand side, with the constraint that the left hand side need to be less than or equal to the right hand side, okay. So this is his whole idea, okay. He compared these two variables, the minimum of RCC1, both are vectors, okay. Okay, the resulting vector based on this operation, okay. Which one is smaller? Okay, this is his key issue, okay. Okay, which means that you know that RCC2 is the minimum one is the most violation if it's still negative value, the most violation based on the decided constraint less than or equal. The minimum RCC1 is original reduced cost coefficient for the primal, okay. And you know that RCC2 is the corresponding reduces cost for the dual model, okay. And which one is smaller, okay. And as long as and also once you know the smaller one, okay, if RCC1 is smaller, okay, you assign those minimum value with their corresponding index, the location of that minimum value in the vector, to this notation, okay, the min RC and index. Or else, or in other case, in a different way, okay, when min RCC1 is less than or equal to RCC1, you move here, okay, to min RCC to min RCC2, okay. Either case, okay, they're gonna execute this routine, okay. Okay, if min RCC1 is less than min RCC2, you go along with the column generation. So this is the column generation routine. But if min else, okay, on the reverse, okay, if min RCC2 is less than or equal to min RCC1, you execute this command, which is the row generation. Okay. In either case, so this is a clever idea that combine these two programs together to execute this. Once, okay, you execute the column generation, you add a new variable, and then you need to update, okay, arrows here because you have new additional variable, okay. But when you add new row here, okay, this is a row generation, this one for the a sub, okay, the a sub here is that you add a new column, but once you have a new column, you need to update the arrow metric also, that you have a new column have been added, okay. And also for the row generation, you have a new row, okay, new constraint, row constraint metric adding to the a sub and b sub. This one with new variable with a sub and c sub, okay, this is n equal n plus 1, and this is m equal n plus 1. But you have to make sure yet this additional, once you add the new row, okay, a new row need to be updated to the a column to use in the column generation also. Okay, so this is a kind of a very good modification, okay. So it's going to switch around by either in every iteration it's going to be either row generation or column generation, depend on the condition here, the min RCC1 and min RCC2, which one is a lower value, as long as it's still negative value, certainly, because once they check, okay, whether which one is good, and when they found that, okay, if min RC, okay, is is greater than, okay, this small negative value, okay, approaching 0, it's going to terminate, okay. Once it's terminated, this program also run for another direct approach here, okay, to solve the problem. Okay, so this is the the way that Dr. Thanapan developed a code and then modify the previous 3 program. I just say the both LP2 and all direct solving. We use the direct solving at the end here. Okay, but as you see that we're not going to waste time to run this program again, okay, because I already ran it in before recording this, okay. We start with the case of 10,000 row and 10,000 variable. The reason is that the main memory still be able to manage to solve all the program within one program. You don't need to run it separately. But actually you should do, okay, because actually these two part, okay, of running the direct model and with the combine column gen and row gen here should be run separately. But I'll show you the results here because we already run it, okay. Certainly it's a long way. You can see that based on the condition here, okay, we already run Thanapan LP both Raj M and N, capital M and capital N. It took around 1 minute to generate the problem, the setup part, the wraps time here, which is the time covering from this statement, the line number 3, to all the setup until here, okay, to line 45. In this case, which is not bad for problem generation, to only 1 second. I think that after several demonstration, you should recognize or familiar the situation that when you're using the Matlab platform as compared to the Excel platform. The Excel platform is took much longer time to setting up the problem, okay? Because they need to communicate, change the format in the Excel format to the original data structure that the program, either LP solver or MILP solver, have been used. Okay, but for the MATLAB, most likely the problem structure is very close to the one that they will use in the solving routine software. Okay, that's why the setup time is it always be much lower. Okay, and they ran it, okay, so many iteration, right? You don't know each one of them. I didn't detect it whether it's column chain or row chain, but this one you can count as ITR. Okay, we will monitor the ITR. And after the first routine run, okay, it took around 5 minutes in my computer to solve this problem. Okay, we because the last optimum solution found here, the elapsed time. For the second part, they start counting the time here, the min, see, which is the row and column. And then the last, once you solve directly, okay, we only use this one, TikTok, okay, to solve the direct model. So the result show here or on screen here, okay. So it's around 300 seconds, 5.5 minutes, okay, something like that, okay, to solve using simultaneous row and column chain to solve. But in the case of the reg LP, it took around 3 times more, okay, almost 900 seconds, which is more than 10 minutes, okay, 15 minutes, around 15 minutes. Okay, so and we expect that actually I didn't show the result that we ran in case of when we start with just 1,000 by 1,000. If you ran for small 1,000 is becomes a small value nowadays. Okay, so 1,000 by 1,000 it the reg approach is faster. I just I didn't have the result to show you, but you can try it in your home in your computers. Okay, and so but at 10,000 it start to show the difference, okay, and it was expected for 100,000 and probably approaching a million, okay, for both M and N in terms of units. Uh, the difference will be much more, okay. And in this case, okay, we only experiment for based on the assumption that we have enough amount of main memory, RAMs, okay, in your computers. But you know that once you have facing a larger problem. So okay, we're gonna challenge you a little bit, okay, by the last slide here, okay. How can we solve this? And we haven't facing the situation of when A is out of core memory yet, with even the size of 10,000 by 10,000, okay. But you might keep adding, increase the value of capital M and N, okay. In this one we use M small m and N, okay. But in the program small m and N is the value that we use for setting up with the sub problem. But in the notation here for the original LP, we remember that we use M small m and N as a full size of the problem in matrix form. Okay, so we going back to this key question here. So and now you already have the tools of based on Dr. Thanapan code here, okay, to solve this problem, but it didn't fulfill the requirement of this problem when A is out of core. What does out of core mean? Out of core means that you keep increasing this. At the same time, I just say that you don't need both of these values need not to be equal. Okay, Since this inequality can be in either case when larger M is when capital M is larger than capital N, or capital M is less than capital N. Can be both case. Okay. Certainly you can try with the sensitivity analysis study of these two parameters. Okay. But at one point, if you keep increasing this value and the problem random generated, you're gonna run out of memory. Just like here, okay, if I just add maybe 100,000 and 100,000, or before we rerun the program again, okay, I'm gonna check you with that ITR parameter, okay. You remember in the program ITR count, okay. So this one, they add that the number of iteration executed within this do while routine, okay. The ITR keep counting the value here, okay, and you know that the result is 927. So it means that you keep solving, but you want to know that how many column gen and how many are row gen. You can check with the final result of M and N. What is a small m? 946, and N is 311. Okay, so there will be more, and you can go back and look at the program here. The program start with M is equal to 10, and small n is equal to 20. Okay, so now you can analyze that. Okay, M start with 10, so there are what, 636, okay, row generation, and n start with 20, so it been 190 or 91, okay, 191 column gen. Okay, when you combine both of that value, you're going to be equal to 927, because it's okay, that pop-up is due to the OpenVPN anyway, okay, because I record this clip at home, okay. So this is how you can analyze it, and whether you check, this is a efficiency analysis, okay, for 331 seconds as compared to 898 seconds. This is efficiency study. Okay, what about effectiveness? Okay, a both approach gives you the same optimal solution. You can see that if you keep running this, okay, the optimal solution, okay, once terminated here, will be stored in X vector and FVL. Okay, FVL. This is the optimal solution. And the last, from the last computation before they leaving this do while loop. Okay, and but in this one, okay, we prepare that the X op and Z op. Okay, this is a direct approach here. Okay, we're gonna, since I haven't created any memory yet, once it's terminated, okay, you can take a look at what is the, I'm not gonna put X optimum solution here. I'm gonna check only C optimum solution, which is 30 the minus value, because this one we working on actually if you reverse the sign of cost coefficient, it becomes plus, okay, because all the cost coefficient have a negative value. Okay, and you know that FVAL is a resulting optimum solution from the do while loop. Okay, as you can see that it give you the same results. Okay, but certainly the resulting X optimum might be different, because they might facing unless that they're unique, only one the optimum solution. But you know, from theoretical LP perspective, you can have the case that when you have alternative optimal solution, but to compare that, it gives you the same objective value. This is one is a minimum value. Okay, so this is effectiveness comparison, that it implies that, okay, we use the same approach, the different approach, but it gives you the same optimal solution. Okay, so but this one is not still not answering this one, what the case of out of core. The outer core means that if I just add, okay, maybe I can try this, okay. I'm going to do 100,000 by 100,000. I should say they need not to be equal, okay. Or maybe I just say that, okay, if I have this case, maybe let's just say only 50,000, okay, concern in here, okay. And I'm going to try to run it, okay. Once I run it, okay, show immediately, okay. That the request of 50,000 by 100,000, you have 37.3 gigabytes array exceed the maximum array size preference. Okay, it means that and you say that creation of array greater than this limit, okay, may takes a long time and cause Matlab to become unresponsive. Okay, actually they didn't accept that they don't have enough memory. They just say that Matlab reaching the uncomfort zone of executing, okay, unless that you have a kind of adding more main memory to your RAMs, okay. There's more information, you can go ahead and read it. So in this case, okay, you might say that we are facing the situation of satisfying with this condition is, oh, okay, I forgot this, out of core, okay, in this case it's out of core, okay, core, okay, out of core memory, okay. And so the key question that how are we going to do this, okay. When you're facing the out of core situation here, okay, you need to use your secondary memory to help you, which can be either your SSD, your thumb drive, or your hard disk drive, okay. And I think I'm not going to solve this problem for you, but leave it as a challenging problem to work on. But we have some recommendation program how to handling I mean to communicate with the secondary memory storage with your program, okay, especially in the Matlab, okay. I have a small program here, okay, called big data matrix storage here, okay. I'm gonna explain this one that like in this case, okay, if you have only small m, or in this one, okay, and you keep in this one we generate in term of a column vector, okay. Aj is a column of vector j, okay, maybe in matrix A, okay. We start with the m, okay, element, it only one column is one. And suppose that you can, okay, just consider one column at a time, okay. If you consider one column at a time, Matlab has a way for you to communicate with the secondary storage by using this command we call fopen and fwrite, okay. F represent file, right? Open the file, write the file, okay. Like in this one, if you start inputting the data column by column, okay. In this case they will only consider, okay, this one column by column, right? In this one we suppose the situation that, okay, the data come one column at a time, which AJI here, okay. When j is equal to 1, which is in the first round of this loop, okay, for j, this is the how to open the file. They will open a file, okay, called a full, okay. This is the A matrix. And with the attribute of w here, w means is write. You start writing the data here, okay. You start writing the data here. Okay, first, okay, they represent the file ID. They open a file called a full to write it down, okay. But if j become the 2 equal greater than 1 here, okay, the difference is that the attribute change from w to a coming from append. Append is mean that you add the new data from the previous data that had been stored, okay. If you keep using the W again, it's gonna write the new data to replace the old one. Okay, so this is the way that for the first time, okay, you open it to write. Okay, once you write it, this one is you write the file here. Okay, you're using the file ID attribute that you already identify here. Okay, either to write or you to append. Okay, you put the AJ parameter here, the AJ data here. Okay, you write here. This one is for the attribute for the precision of your data. Since this is the numerical data, okay, we store this one we call single precision. A lot of time this might not be enough. You put the other command called the double. Double is mean that you double the number of bytes, okay, to represent this data. Okay. If you want more accurate data to be stored, you might change this to double. Okay. And certainly when you execute all mathematical operation based on double precision, okay, it's going to take more times. Okay. And then once you write the data into this file name, okay, a full, okay, you close it first. Okay, you close it. The reason that I just say that, why don't you keep continuing to write? You don't need to worry about it. Okay, I think that it's because you're dealing with a very large, in terms of large number, it's out of core. So once you save the data, you want to reset okay, the memory like this one. In every time, instead of I store them, I cannot suppose that I cannot store the metric of size m by n. Okay, but I just can input the data one column at a time. This column might be okay, open and call and read. There's another statement we call fread. Fread is when you read the data here. Okay, fread, you read the data here. Okay, and in this one, because you know that m and n is enough. Okay, it's not the large value, so we will to okay read all the data. Okay, with the precision attribute and with the size of matrix m by n. Okay, and put it back to the original A matrix here. Okay. But again, if A cannot be stored, it's out of core if m and n is become too large. Okay, fread might try to read for some portion of the data. Okay, and working on it in the memory once at a time. Okay, so this kind of demonstration should be enough for you to continue to adjust, just like what Dr. Thanapan did with my original here of the first original tree program of IP direct solving many variable and many constraint here and all together to become this part. But this program still not answering, just like what I told you, that the hour call. When you facing the hour call situation, okay, sorry. You need to make sure yet that you okay, you know how to communicate with your hard disk or your secondary storage. This is the example of the file that you can open the file and then you can just put the very big data, okay, that out of core in the main memory, okay, into your secondary storage using the fopen with either write or append the value, and then you can use fread, okay, and to reopen the file. But actually you don't need to get it all out. Okay, this one we get all the value that we've been input in. You might try to take down only a partial value, okay, to put it in this metric. Okay, this is fit with the approach that you are trying to do with this program. Okay, so if you be able to adjust it, okay, but the price you have to pay is certainly that it's gonna take longer time to execute all those fopen, fread, and fwrite, because once your data is in the secondary storage, it's not as quickly executed as your main data is in the main memory. Okay, that's the price you have to pay. But certainly the efficiency will be less, but uh, if you don't have a large sufficient computer CPU or memory, okay, to handle the problem, okay, as I show you that it cannot even start solving anything, okay, when you facing that situation, okay, this might be the only way that can help you, okay, and I will leave this, okay, as a challenging problem to all of you, okay, if you want to try to work on this, but you might answer me in a different way, that I rather add more main memory, maybe add the RAM more. But you know that if you study the hardware architecture of computers, especially the CPU, central processing unit, okay, at one point it doesn't matter whether you add more main memory in them, okay, the CPU will just stop there, okay, it become redundant, okay, it doesn't matter, okay, so there's a limitation also for when you adding the RAMs or the amount of RAMs in your main memory, okay, so but who knows that with the quantum computing, whatever they're working on in hardware configuration research, okay, the architecture research, okay, and one day this might not be a key problem. It actually is not the key problem now today anyway, because you might say that you can keep adding the amount of both main memory and secondary memory to handle this problem, okay, and maybe the time to execute communicating between secondary memory and CPU may be much faster in the future, okay, that reduce the obstacle of using this approach in terms of reducing the efficiency of the approach, okay, and another key problem that you can do in this issue is that now we stick with the Matlab okay platform, okay, what about we going back to the Excel platform, okay, which many key, there's two find of problem and solution, okay, with too many variable and too many constraints, okay, for you to work at. You might try to work on the what we call the VBA, okay, macro. But for the Excel part, it would be uh, much more difficult in terms of efficiency, okay, as you already seen in the previous example, and also when you both have too many constraints and too many variables uh, simultaneously at the same time, okay, it means that in terms of our core situation, it means that one Excel file is not enough, okay, to suppose that you have one file that contain a partial of the problem, because you cannot store, okay, the whole uh, because once you open that file, okay, the memory is not enough, okay, within for as we have already seen in the Matlab situation, that it means that you cannot take all the data from the problem, okay, to work in your memory at the same time. So, so to simulate this situation in your Excel environment, you need to create a couple of files, okay, to store the problem. For example, okay, you decompose the problem and store in 5 Excel files, okay, and then you open one file as a working file, okay, that you partially, okay, import the data from each of the uh, input file that store the decomposed problem separately, to work on the working file on just for the uh, what we call both either row generation or column generation in that working file. And then once you get the result from that working file, you need to uh, export the results, okay, to check with the original input file for the optimality condition, okay, in both the RCC1 and RCC2 as represented in the Matlab software. And then it can be either case of the row generation and column generation, and export the data from when you're checking the whole problem, and export the result can be either the new row generated or the new column generated, put it back in the working file and work on and off like this. Okay. Okay, and one situation that I should mention to you in the Matlab that that go beyond the idea of Thanapan here. Okay, the idea of Dr. Thanapan is that you alternately check with this condition of the minimum RCC1 and minimum RCC2. Okay, but there are some other way they can approach to solve this problem also. That for I give you an example that suppose that you can, okay, you're starting up with the small n, okay, the limited number of variable first, and then you consider solving for the too many too many run this program first, okay, row generation, okay, by picking only small n, okay, but considering the whole m, okay, and you run it until you get the optimal solution. So that optimum solution is the optimum solution according to, if you consider the Thanapan program is according to the A row here, the A row here. Okay, solving for the optimum solution for the A row as a full problem. So you're gonna, first of all, you limited the number of variables first, okay, for consideration, and considering all possible all constraints, okay, capital M, and you ran it as row generation until termination. So it's gonna keep adding the new row, okay, for you. So you're gonna switch it. It's not gonna keep switching back and forth just like what Thanapan did, but they keep adding the row first with the limited amount of number of variable until the final iteration for the row generation, okay, and then you gonna get moving back to the column gen. Is that you have to, okay, use the final result from the row generation and be able to estimate the whole dual solution, okay, for all the possible rows, okay, or constraint, okay, and check with the column generation whether that's a global check, that is there any new additional column generation, a new column that if you add it to the row generation routine, that gonna help solving the problem, help improving the solution. Okay, so it start with row gen, run until termination, okay, and then export the results, okay, of the dual price, check with the new column globally, okay, for the whole problem, and add that column to the row gen profile and rerun the row gen again. So the row generation is the main part of the problem, and then keep running iteratively, okay, uh, and then for each iteration, once row generation terminate, find a new global column and add it and rerun it again until the column generation satisfied that there's no additional column. So you get the optimal solution. Okay, so you see that it's not gonna switch around with just like what Thanapan approach is. Okay, on the reverse way is that you might start with column generation. You have limited model, but you consider all the possible column. You keep adding the column, okay, until termination for that subproblem, limited number of rows. Okay, and then you switch back to the row generation, check the redundancy of the remaining row constraint. If there's still violation, okay, you add that row and rerun the column generation again. Okay, so there will be two different approaches than what Thanapan did. It would be interesting if you can compare all these three approaches and also compare with the direct solving. And our expectation is that with the additional idea of this program of how to handling the big where is that? Oh, okay, over up here. The big data matrix storage here. Okay, combining with this idea. Okay, I couldn't add this. Okay, here. The key question for all of you is that is it possible to apply this approach or either find either one of the three strategies? But certainly there'll be a couple more strategies that you can adapt from that idea. Okay, from those ideas, that at least three ideas, that the Thanapan idea and the other two approaches that I mentioned to you, that can we solve up to the size of m and n up to 1,000,000 units. Okay, which means that if you look back at the program here, I might say that is it possible to solve this case when both m, capital M and capital N, reach the million unit? Okay, so that'll be challenging, quite a challenging problem to solve. Okay, but we and also the Excel, if we do it, can we do it under the Excel platform also? That can be another question. Okay, so this is a tremendous research problem for all of you to try to perform and investigate if possible. Okay, I'm gonna end this session here, and next time we're gonna start looking the application point of view of this problem, because so far, okay, we have been just using the randomly generated problem based on the mathematical structure, okay, starting from clip number 25, okay, but in the latter clip after this, okay, we'll start giving you more of the application aspect, that what kind of problem in the real world that similar that you're facing have a similar structure than in the mathematical structure that we've been discussing so far. Okay, so we end up here and see you then in the next clip. Okay.